In today's video, we will talk about the tangent plane, define what it is, and derive its basic properties. Okay. Let us first consider what we have in plane. So, okay, let us recall that in plane, okay, the set of all pairs x of t, y of t, where t is changing in an interval, this could be all real axes. This set is a curve because okay, you can think of t something like time. So this gives you the following. At t0, at some point, okay, when t is t0, you have x of t0, y of t0, which is a point in plane. Okay. So this is when t is t0. Now if I change my t, I will get a different point. So I will get x of t, y of t. So I have at t here. And this will go on. When t changes, I will get different points. So throughout, I will end up with a curve. So I can call this the curve gamma. Okay. This is the so-called parametric form of a curve. Okay. Now, when we look at this curve and assume x and y are differentiable functions of one variable, that is, they have their derivatives, okay, then we can talk about a tangent line to this curve. Okay. Obviously, this is easy to see. Then okay, the curve gamma has tangent lines drawn to it. Say at t is t0, okay, we have the tangent line y is mx plus m. Okay. Of course, we have a certain slope, which is the derivative of the function, and so on. Now, this is the equation of the tangent line, and x of t, y of t is a representation of the curve. Thus, we end up with the following. Let me see. So we have the tangent line, and so yeah, we end up with dy by dx is m. At, of course, t0, which means we are at some point. Okay. Now, okay, chain rule tells us that the derivatives here then that's to say dy by dt at p0 again is the derivative of y with respect to x and derivative of x with respect to t. In other words, this tells us that m, that is y prime t divided by x prime t, holds. Okay. Now, since the vector 1m is parallel to the tangent line, it follows that I can write my v as 1 y prime t divided by x prime t, or 1 over x prime t, x prime t, y prime t. Now, this tells us that because v is parallel to the tangent line, we conclude that the derivative at any point is parallel to the tangent line. Now, this is a very nice result in the sense that we can generalize this notion to curves in space. Okay. Well, this is just an introduction to tangent planes and not a lecture on curves. We will discuss these things later in detail. But for the time being, just note that the notion of tangent line to a curve, which can be written as x of t, y of t, and z of t, of course, in space, is defined to be the line parallel to x prime t, y prime t, and z prime t at t0, and passing through the point p0, which is x of t0, y of t0, and z of t0. Now, with this introduction, that is, if we have a curve x of t, y of t, z of t in space, okay, then the vector of derivatives is parallel to the tangent line drawn to the curve. So with this information, now let us do the following. Now consider a differentiable function f of xy, and actually, okay, given by, let me say, the implicit formulation f of xyz is 0. Now, this is a surface given implicitly, all right? Okay. Now, consider any curve on this surface. Okay. To make this more understandable, I will make a picture in a minute. Consider any curve on this surface. Of course, passing through a fixed point. What does this look like? It's something like this. Okay. I have a point x0, y0 here. And somewhere on top of that, I have my surface f of x, y, z is 0. Okay. And here, I have a curve. Okay. Gamma is on the surface. Say gamma is given by x of t, y of t, z of t. Okay. Well, because x of t, y of t, z of t, that is gamma, is on the surface, gamma satisfies the equation of the surface. Okay. In other words, we have this. F of x of t, y of t, z of t is 0 for every t. Now, if this is true and f is differentiable, then we can differentiate. So, differentiate here means, of course, t is the variable, so we have the total derivative. Taking derivative, d by dt, we get the derivative of f with respect to the first variable times x prime t f2 y prime t f3 z prime t, all evaluated at t0, and this is the derivative of 0, so it is 0. Now what does all this tell us? Now this is a dot product actually. So this is nothing but f1, f2, f3 at p0 dot x prime t, y prime t, z prime t at p0. Okay. But this is a vector parallel to the tangent line, to the curve gamma. Now, this is actually the point where we want to concentrate. This tells us, so this vector, f1, f2, f3, at p0, okay, which is independent of the curve. This is only something about the function f, its derivatives, and the point. So this, which is independent of gammas, okay, is perpendicular to the actually tangent lines, okay, to all gammas on the surface. through P0. Okay. Well, since these curves are on the surface and they do pass through P0, okay, this means that all the tangent lines, okay, to curves through P0 lie in one plane, which is the plane through P0 and with this normal. Because all of these tangent lines are perpendicular to the same vector. So, conclusion. Okay. The tangent lines drawn to any curve through P0 on the surface okay, lie on one plane with normal vector F1, F2, F3, and passing through P0. Now, this plane is called the tangent plane. To fxy equal to 0, fxyz equal to 0, at p0, x0, y0, z0. Well, immediately we get its equation. Okay. So its equation is P minus P0, let me say x minus xyz minus x0, y0, z0. This is P0. This is P dot F1, F2, F3 at P0. Which is the normal vector, okay, is equal to 0, of course. So this is the equation of the tangent plane. Okay. We have some remarks, though, before we proceed to calculations. Okay. Okay. Well, the first remark is the following. Well, we use the total derivative formula to show that there is a tangent plane. There is a single plane where all tangent lines to curves on the surface lie on. Which means that we assumed differentiability. So, the first remark is that to define the tangent plane, we assumed, okay, f is differentiable. Actually, capital F is differentiable. At P0. Okay. So we cannot define a tangent plane if we don't have differentiability. actually one can show that these are equivalent. Namely, okay, a geometric definition of tangent planes, okay, says that tangent plane at P0 exists if and only if f is differentiable, or rather capital F is differentiable at P0. Well, this geometric definition also uses the limit again. So this makes perfectly sense in the following manner. In one dimension, we already know this. That is, you can draw a tangent line to a curve in plane if and only if it is differentiable, which means it has a derivative. So in one dimension, this is well known. So we already know this. In one dimension. Or rather, let me say in plane. Okay. So this is a perfect evidence that differentiability is the correct substitution or generalization for the derivative in plane. Okay. A second remark is that if the surface is given explicitly, say z is f of xy, then, okay, obviously, this is an implicit form. So, okay, if f is differentiable, okay, implies that tangent plane exists, of course, but the equation of the tangent plane is then p minus p0 dot the derivatives of f. Well, what are the derivatives of f? f1 would be del f, del x. fy would be fy. And derivative with respect to z would be minus 1. So this is the equation of the tangent plane. Well, this becomes a normal vector to the plane, to the tangent plane. Of course, the normal vector is not unique. Okay, we can take the negative of this. For example, minus f sub x, minus f sub y, and 1. Or any multiple, it doesn't matter. The characterization of the plane does not change in that sense. Okay. A notation. One shows the vector f sub x, f sub y, f sub z by an upside down triangle f. Okay. called the gradient. All right. Okay. Well, it simply means you put all the partial derivatives, okay, according to the order of the first variable, then the second, then the other, etc. Okay, and you form a vector of partial derivatives. Now, this also plays an important role, we will see quite soon, but this is defined independent of the dimension. So, if we only have fxy, okay, from R2 into R, then, again, gradient f simply means f sub x and f sub y. Okay. But you can generalize it to Rn as well, which we will not do here. Okay. So the gradient is a short way of writing this sequence of partial derivatives. And therefore, okay, thus, if okay, f, respectively, this f is differentiable, then gradient f, or, okay, well, I will not repeat actually that, f sub x, f sub y, and minus 1 at p0, okay, is a normal vector to the tangent plane. Okay, drawn to the surface at p0. Okay. We will be using this notation quite a lot, and it will make our jobs easier. Okay, let us now pass to some examples. Okay, let us find the equation of the tangent plane drawn to x squared plus y squared plus z squared is 4 at the point p0, which is 0 square root 2 square root 2. Okay. Well, to start with, this function, x squared plus y squared plus z squared, our capital F, okay, is a differentiable function because it has all its derivatives, and those derivatives are continuous functions again, because this is a polynomial. Okay. Firstly, then, our f x, y, z, x squared, y squared, z squared minus 4 is differentiable. Okay. So we can proceed with the formula we derived. There is a tangent plane, and so on. Now, okay, a normal, okay, is n, that's gradient of f, at p0. This is nothing but 2x, 2y, and 2z at p0, which happens to be 0, and y is root 2, so 2 root 2, and 2 root 2 again. So this is a normal, because we don't care about this 2 root 2 here, we can put there 0, 1, 1 if you want. Okay? So that would be our normal. So the equation would be p minus p0, that is, let me write it in explicit formulation, p minus p0, that is 0 root 2 root 2, dot 0, 2 root 2, 2 root 2. Okay. This should be 0. Okay. Now what does that mean? We have x, okay, dot 0 plus y minus root 2 dot 2 root 2 plus z minus root 2 dot 2 root 2 is 0. Or equivalently, you don't have any x's. You can cancel these. So it says z plus y is 2 root 2. So this is the equation of the tangent line that we have there. Okay. Now, let us use the same argument for the case in plane and see that we really get what we expect. That's to say, find the equation of the tangent line drawn to x squared plus y squared is 1 at p0, that is 1 over root 2, 1 over root 2. Of course, this is a point on the circle, and we want to find the equation of the tangent line. Of course, we can do this using our 119 methods, but here we want to do it a little bit differently. So, since tangent plane is the generalization of tangent line, okay, in plane, okay, we have the following. We have the equation of the tangent plane being the same as the equation of the tangent line. In other words, here, if we say this is the gradient, this is the function, okay, fxy, and it gives the implicit formulation, okay, for the circle, then we have p minus p0 dot the gradient of f at p0, which happens to be 2x, well, x is 1 over root 2, and 2, 1 over root 2. 2x and 2y, well, x, y are these, so this is that, and this is equal to 0. So this is the equation of the tangent line. Well, is it really so? Let us check. Okay. Well, let me not say check, but let me simplify it first. That is, okay, we have x minus 1 over root 2, okay, times 2 root 2 plus y minus 1 over root 2 times 2 root 2 is 0. Of course, here I can use 1, 1. Yeah. So that says, canceling these things, I have x plus y, okay, that is minus 2 over root 2, so that's minus root 2, it's equal to root 2. Okay. So this is the equation. Well, check it from earlier methods. check it directly by calculating y dy by dx, that's the slope, and so on, and so on. Okay. Now let us consider a slightly more complicated example. Where we will use a little bit geometry. Okay, we want to find the equation of the tangent line, okay, drawn to the curve of intersection of the surfaces x squared plus y squared plus 2z squared is 4, and z is e to the x minus 1. Okay. Now, a remark here. Okay. Since a line is the intersection of two planes, a curve in space is the intersection of two surfaces. Okay. So a line is a special curve in space, and so a curve in space is the intersection of two surfaces, which is exactly the situation here. This, of course, tells us that a curve equation is also given by two equations in space, just like a line equation. Now, what do we have here? Well, we have two surfaces intersecting. So, roughly, we have a surface and, say, another surface. Okay, and they intersect. Well, say we don't see this one, it's behind this. So this is one surface, this is the other one, and they intersect, give us some curve, call this curve gamma. Now, we see that because this curve is on this shaded surface, its tangent line must lie on the tangent plane drawn to this surface. Okay. So let me show this with a point. P0, and call this the tangent line T. Okay. Now, by the very observation we had at first, okay, T lies on the first surface. Let me give names to them. Say this is the surface pi1, this is the surface pi2. So T lies on pi1, not T, but gamma. Gamma lies on pi1, so its tangent line lies on the tangent plane. actually, I should give a point as well. We can calculate that in general, but maybe I should say at P0. Okay. So we have a P0 here, and gamma lies on pi 1. So its tangent lines, line lies on the tangent plane drawn to pi 1. At P0. Now this tells us the following. Because T is on the tangent plane drawn to the first surface pi 1, okay, it must be perpendicular to the normal of the plane. So T is perpendicular to the normal of the plane, which is the normal, okay, to the tangent plane, to pi. Okay. But gamma also lies on the other one. So gamma, so T, is perpendicular to N2, which is normal to pi 2. Normal to actually tangent plane. To pi 2 at P0. So this gives me quite an insight, that is, this T, the tangent line to gamma, is perpendicular to two vectors, which we can calculate. So I can take it to be a cross product. It's perpendicular to both vectors. Okay. So we can take VT, okay, parallel to the tangent line as N1 cross N2. Okay. We are only looking for a vector perpendicular to both of them, and we can get one by taking the cross product. Well, before that, let us calculate N1. Remember, N1 is the is a vector perpendicular to the tangent plane drawn to pi 1. And pi 1 is up there. It's an ellipsoid. Okay. So we can take it to be the gradient of the function x squared plus y squared plus 2z squared minus 4. Okay. At P0, of course. So it is 2x, 2y, and 4z at P0, which is the point 1, 1, 1. So it's the vector 2, 2, 4. Similarly, N2 is the gradient of e to the x minus y minus z, because it must be equal to 0. So it is, okay, at P0, so it is e to the x minus y minus e to the x minus y, and derivative with respect to z at P0. So it becomes, at the point 1, 1, 1, e to the 0 minus e to the 0 and minus 1. So dt can be taken as the cross product of n1 and n2, which happens to be the determinant of n1, which is 2, 2, 4, and 1, minus 1, minus 1. Well, this happens to be, I will not calculate it in detail. Okay. That would be plus 2, and then that would be plus 5, and this would be minus 4. Is that correct? Probably not. Let me see. That's minus 2, minus 4. That should be 6. Okay. Now, T has this parallel vector, and it passes through P0. So equation of T would be P is equal to P0 plus T, okay, 2, 6, and minus 4. Of course, you can forget the multiple 2 over there. Just say it's 1, 3, minus 2. So this would be the equation of T. Okay. Well, obviously, another argument which can be used here geometrically is that the tangent line to the intersection curve lies on both tangent planes. And therefore, it's the intersection. Okay. So this would be an alternative way, where you don't have to find the normal vector as it is. You can formulate it in a symmetric form of the line equation. So let me just comment on it. Alternatively, T lies on both tangent planes, drawn to pi 1 and pi 2 at 0. So it is their intersection. Okay, so find these tangent planes and intersect. So this would be an alternative solution to the same problem. Okay. As a fourth example, let us find the points are the tangent planes parallel to the xz plane, okay, where the surface is given by x squared plus 4y squared plus 16z squared minus 2xy is 12. Okay. Well, now, note that two planes, the tangent planes and the xy plane, are parallel, means that their normals are parallel. Okay. So since parallelity of two planes means their normals are parallel. Okay. We get, okay. Well, what do we get? At the point x, y, z, okay, the normal to the tangent plane drawn to this surface, well, we know it's the gradient, okay? We get n, that is the gradient of f, that is x squared plus 4y squared plus 16z squared minus 2xy minus 12, okay, is parallel to the normal of the xz plane. Well, the xz plane is the plane exactly where y is 0, okay, and a normal to it is j. It's a normal to xz plane. So we get the following. Well, in the gradient, we get, of course, let me say, the gradient of f here would be 2x, derivative with respect to x, minus 2y, and then derivatives with respect to y, 8y minus 2x, okay. And finally, derivative with respect to z, which is 32z. Now, this is parallel to the vector j, which happens to be 0, 1, 0. The j vector. Now, this, of course, is a vector equation, but it tells us three things. It tells us that 2x minus 2y would be 0, and 8y minus 2x would be lambda, and 32z would be 0. Okay. Now, of these three equations, which must be solved simultaneously, okay, the second one gives us the value of lambda once we find x, y, and z. So, these tell us that x is equal to y. That's the first equation. The second one, okay, this helps us to find lambda, but we are not interested in lambda, in which we are not interested. And, of course, the last equation says that z is 0. All this tells us, okay, that the points must be of the form, well, x is equal to y, so it's xx, and z is 0. So these are the points. But of course, we have one more data. And that data is that this point is a point where a tangent plane is drawn to the surface. So it must be on the surface. So now, this point must be on the surface. Since the tangent plane is drawn at that point. This means that, okay, putting the point in the equation, that is, substituting xx0 in the surface equation, we get x squared plus 4x squared, x is the same as y, plus z is 0, minus 2x squared is 12, which says that you have 3x squared, so x is plus minus 2. In other words, there are 2 points in question. The first point is 2 to 0. The second point is minus 2, 0, because x and y are equal and z is 0. So at these points, if you draw tangent planes on the surface, well, of course, they satisfy the surface equation. And you get tangent planes parallel to the xz plane. Okay, why at 2 points? Well, geometrically, we expect this because the surface, okay, if you look at the surface, it is x squared plus a multiple of y squared plus a positive multiple of z squared, and you have an xy term. Now, the product term signals that there is a rotation process. So for getting it, we see that it's an ellipsoid. Okay, so if we have an ellipsoid, okay, something like this. Okay. And if we have a surface here, a plane, that is the xz plane, and we are looking for tangent planes which are parallel to it. Of course, you can check that maybe somewhere here you have a parallel tangent plane, and on the other side, somewhere here, you have likewise a tangent plane drawn at this point, and they are all parallel. So there are 2 points. Okay. In an ellipsoid, you have only 2 tangent planes at 2 different points in that sense. Okay. Now, so much about tangent planes. You will have plenty of exercises in your textbook about it. I urge you to work on those problems because only then you will master the calculations.